Okay, so next up, we're going to do a multiple regression. And we have a data set here, and it's basically, I think you should have seen this data set before. It's different colleges, the type of college, and then some kind of statistics about the college. So we have the median SAT, the acceptance rate for the college, the expenditure per student, and the proportion of people graduating in the top 10% of their high school. So I think this is a real world data set, if a little bit maybe dated, I'm not sure. But you can see, for example, where's Harvard? Harvard, yeah, has a very low acceptance rate, and 90% of students in the top 10% of the high school. And we'll see if we can predict graduation rate from these other kind of quantitative variables. So let's go to data analysis. We want to go, we were previously on the histogram. We want to go back to the regression. Okay, so the Y is going to be graduation rate. And the X, this is very kind of unsophisticated in the way it tracks variables. Your X's need to all be in a block together. So quite often, if you're choosing subsets of the variables, you have to do a lot of copying and pasting and rearranging. But here we are. We have the Y's and we have the X's. Um, and then what we're going to do is we're not going to bother with anything else, except we're just going to have the residual plot. We're going to look at the residual plot because this is predominantly going to be, we're going to be looking at output. And we don't want it in F1 because that's going to overlap with our data. We'll put it here in J3. Okay. So let's just actually, we've got multiple residual plots for the different x's. But first, like, look at some of these statistics. Now, the first thing is, again, we have the R squared. So this is the total amount in the y proportion of variance in the y accounted for by the x. So we've already done this a few times. The R squared here is 0.53. We have the adjusted R squared, which accounts for the number of variables in the model. Now, the next thing is the ANOVA table. Now, if I teach this in one of my actual stats classes, I spend a lot of time going through and building this all up. But basically, there is a test, a statistical test, and let me just take a snippet of the screen. And so the null hypothesis is that all of my regression coefficients are equal to 0. So B1 equals B2 equals all the way up to where K is the number of coefficients. They're all equal to 0. And my alternative hypothesis is at least one BI is not equal to 0. No, that's not all of them. Not all of them. At least one of them. So this is just telling us there's something useful in our rejection model. And in fact, we're not going to worry about the F statistic. We could reject H0 if F is greater than a critical value of F, but we don't get the critical value of F. So we basically have this F distribution, which looks a little bit like this. And we have some significant value, F alpha, with the alpha to the right. But we also have a p-value associated with my F. So we have my actual F here. And as our F gets bigger and bigger and bigger, the F is just a measure of how much variation is due to the regression relative to how much is due to the error. And as F gets bigger, we get more and more to the regression and less to the error until eventually we get to, say, a stage where this is my p-value to the right of the f, we're going to reject H0 if p is less than or equal to alpha. And again, I can, if anybody's interested, I can chat and go through the theory on this in a little bit more detail. But for this class, you just know we've got this what we call an omnibus test here, that there's something useful. The bigger the f, so the bigger the f and the lower the p-value, the more significant. And we're going to reject H0 if my p is less than alpha. So say, for example, we did our standard alpha of 0.05. Then we reject H0 and say at least one beta I is not equal to 0. Now also, for all my beta i's, we have the individual t-tests. So we'll have, like, a t-test here. If this was, say, for example, beta 1, beta 2, beta 3, and beta 4, we would say, for example, reject H0. We'd have H0 beta 1 equals 0. Beta 1 is not equal to 0, etc. So, it's just back to the thing of me telling my boss, yeah, this regression is useful. I'm not quite sure what's useful. Then I want to look at these individual tests and the individual p-values for these tests. Now, you see here, let's go back to our thing. We see here that all of our p-values are less than, say, for example, we set alpha equals 0.05. All these are less than 0.05. So we can say that if we set our alpha as 0.05, then all 4 of these are significant in the regression model. So let's just again say that, let's just snip it again. Say that we have, our y equals beta 0 plus beta 1 x1, where x1 is the median SAT, beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus our error. And then we've estimated with these values, the coefficients. These are estimates of the betas. You could call them B0. I tend to use beta hat. And let's just kind of go back and go through what we did in the book. So say, for example, here, we have these kind of coefficients. Let's just say, for example, let's just imagine we had some new data. So we put new data down here. And we want to predict the graduation percentage. Median SAT, acceptance, expenditure, top 10%. And we're looking now at the example on kind of example 8.12. So say, for example, we had a college with a median SAT of 1,300, a 20% acceptance rate, expenditure per student of $40,000, and top 10%, 80%. We could actually predict the graduation rate as follows. It's going to be the intercept. So it's going to be this, the estimate of beta 0. And just in case I want to drag, I'm going to put some dollars on there. Plus, and I'm not going to use any fancy functions, some products. I'll just say it's going to be the SAT times the beta 1 Oops. Plus the acceptance times the beta 2 plus the, where are we? Expenditures times the next beta plus the top 10% times the coefficient. There we go. Okay, something's got a bit wrong here because we have a graduation rate of 438%. Let me have a look. Aha. Median SAT is not 13,000, it's 1,300. Okay, that doesn't look any better, but let me just think. The acceptance rate was a percentage. So let's just format this as a percentage. And yeah, we basically had we had 20 instead of 0.02, and this looks more realistic in terms of the data. So this gives us the graduation rate. And we could actually do, for example, 1,400, maybe, but maybe a little bit less acceptance rate. We got 40%. And expenditures 30,070. And then we could just drag down. And again, we've decided we've got a higher acceptance rate, but we also have a better SAT and less in the top 10%. And we have a graduation rate of 93. And let's have a final think about the interpretation here. So the intercept, this is the kind of the graduation rate when all these other values are 0, which again is not particularly meaningless. It's outside the range of the data. For one increase in median SAT, the graduation rate kind of goes up by 0.07. Assuming when we do this, we assume that all the other variables, all the other independent variables are held constant. With acceptance rate, the acceptance rate increases by 1, then the graduation rate decreases by 24, and the expenditures goes up by 1, which is a little bit counterintuitive. Then we have this very small decrease in graduation rate, and top 10% of high schools goes up. Then the graduation rate goes down a little bit. And again, it's quite hard because the way these variables interact with each other, we'll talk about this in a minute, they're all quite highly correlated with each other, which sometimes means that you get results that don't always give common sense because there's kind of a strong interaction between the variables. But anyway, I think this worked as a simple interpretation exercise. We'll just have a quick look at the residual plots. These look pretty good. We don't see any, we're pretty constant. We don't see any heteroscedasticity. We don't see any real deviations from linearity. And we don't really see any kind of significant autocorrelation, i.e. high errors in one area of the graph and very low errors in the other area of the graph. So these actually look pretty good. Okay, that's it.